vertical asymptote. But as you might imagine, if we have vertical, we can probably have others. And what we're going to do today is we're going to look at the end behavior of rational functions. And we looked a little bit at the end behavior of the polynomials in our last unit, and now we're going to look at them with respect to the rational functions. And so for the first one here, we're going to type these in, and luckily I have them typed into the calculator already. But if you would like to follow through, you know it's a lot easier to type them in at your desk than it is up here in the smartboard. So our first function is f of x equals 8x divided by 5x squared. And if we type this in and we hit graph here at some point, we get a picture that looks like this. And we just want to draw a real rough sketch here with that. And when we draw a rough sketch of that, we get something that looks like that. And if we type in the second function, I'm going to go back to y equals here, and what I'm doing is I'm hitting enter on the equal sign. And when I hit enter on that, the function's still in the calculator, but it won't graph. So now I'm going to highlight this equals by hitting enter, and this will graph our second function, which looks like this. And then real quick here, yep, just to make sure. We get a picture that looks like this. And then thirdly, what we'll type in is we'll type in the negative 2x divided by 9x to the 6th. And when we do that, I'm going to go back and unhighlight that function and highlight our last function. And we get a picture like this. What we've got down below here is we've got something that says conclusions for case 1. Well, I knew that I was going to have trouble typing these into the calculator, which is why I have them in already. But if I unhighlight, or if I highlight, whatever the case may be here, and print all three of these, the question is, what's happening to our function as x approaches infinity, or x approaches negative infinity? So in other words, as we go towards the right, as x approaches infinity, what's happening to all three parts of our graph over there? What are we getting very close to? Getting very close to the x-axis. And if you look as x goes to negative infinity, what's happening to our graphs there? We're still getting very close to the x-axis. So what happens to the y values as x approaches infinity and as x approaches negative infinity and positive infinity? Well, what it looks like is that the graph levels out at y equals 0. And I think that the calculator in particular on this example shows that pretty well. I don't know if this will be confusing for people that are watching the video after the fact. but I think that you can see that a little bit better than on some of the other examples. So as I scroll through here, there's three cases that we're looking at. We're looking at the first case, the one that we just did, which is where the numerator degree was less than the denominator degree. If I go back here to our examples, we had x to the first in the numerator and x squared in the denominator. X to the first in the denominator, x squared in the denominator. That's x to the first in the numerator, x squared in the denominator. And we had x to the first in the numerator and x to the sixth in the denominator. Our numerator is less than the degree in the denominator. Call that bottom heavy. The second situation is that the degree in the denominator is equal to the degree in the numerator. And on the first problem here, the f of x function in particular, I do need to take a couple of minutes and look at this one. Because maybe you see, and especially after just going over our homework, that we have removable discontinuity in this one. Because our x squareds would cancel out. Because our x squareds would cancel out, remember, to get that removable discontinuity, we would have said that x squared doesn't equal 0, was how we actually would have started it, which ultimately would have meant that x doesn't equal 0 would be our domain. However, because the x squareds cancel out, we would have a removable discontinuity at 0 and then when we put that value back in, the only number that we have left is a 3. So if you did take the time to type this in your calculator, Thomas?
Well, would it be 0, 0 because 3 times is 0?
But this value would have already canceled out. So you can put whatever value you want in there, it's not going to show up. It's already canceled. So in other words, here, what the picture looks like on your calculator is it looks like a horizontal line, but our removable discontinuity would be there. There's actually an open circle there. And just in an effort to save time here, if we typed in this next graph, it will look like this. But I know you're not getting that put in your notes right now. And then when we type this one in, we get that. And I'm going to cover this up now. I hope I can't cover it up. I was hoping that I could. But I'll put that one there. So we can maybe get our open circle. There we go. Well, what we're looking at here again is what happens to these y values as x approaches infinity and x approaches negative infinity. Well, I think it's harder to see on this one, but what it looks like here is that we've got a horizontal line somewhere in our graph, and I need to show this on the video so people can see it, somewhere, if I can get it a straight line drawn in here, or somewhere right about there. And we already have the horizontal line on our f function, but ultimately what's happening to the y values as x approaches negative infinity and x approaches positive infinity? Well, what happens is that our graph, let's capitalize the G, our graph levels out. At y equals a over b. And this is a situation where the numerator degree and the denominator degree are the same thing. So I want to skip to the end here, even though I haven't done all of them, and I will come back in a few minutes in the video and finish the case 3. But what we have at the end here is, in order to determine additional asymptotes, because there's more than just vertical asymptotes, we can look at the end behavior and we can come up with the 3 cases. There's a case where bottom heavy, where the degree on the bottom is bigger than the degree on the top. If we have that situation, we have a horizontal asymptote at y equals 0. If we have the same degrees, then we have a horizontal asymptote at y equals a divided by b. And we'll look at an example here, and if not now, a little bit later. And finally, the case 3 that we didn't type in, but I will have in the video in a few minutes, is if it's top heavy. If the degree is a greater degree on the top than on the bottom of the fraction, then we have what's called a slant asymptote, which is what the third cases look like if you happen to type them into your calculator at some point. So what we're going to do to calculate out these values is we're going to isolate the terms that determine the degree. Then we're going to simplify. And then we've already kind of sketched, so I won't spend the time on that. But we want to come up with what we've got in terms of asymptotes here, in terms of horizontal or oblique. So for instance here, if I follow through on the steps, what it says, isolate the terms that determine the degrees. Well, in our numerator here, we have 5x squared. That is going to be degree 2. In our denominator, we have a 3x. The degree on that term is 1. If you notice, the degree is coming from the exponents. X squared, degree is 2. X to the first. So what we see from here is that the top of the fraction is bigger than the bottom of the fraction. So this is a top-heavy function. And when it's a top-heavy function, if we go back and look at this, it's top-heavy. That means that we have an oblique asymptote. So we follow that same procedure here on v of x. Let's look at our degrees, and our degrees are determined by the variables here. So our numerator is 7x cubed, and that means that our degree is 3. Our denominator, we have negative 2x cubed. That means that our degree is 3 again. Notice that in our rational functions that we're lucky enough that our terms were in descending order. But what we see when we look at these is that we have the same degree on the top and on the bottom. And because of that, when we look back at our chart here, the horizontal asymptote, we have a horizontal, and it's going to be at y equals a over b. Well, the a is coming from the 7, and the b is coming from the negative 2. And technically we don't like the negative in the denominator, but it is what it is. On letter C. Once again, look at what we've got. Our numerator, we have 2x cubed. That means degree 3. Our denominator is 5x to the 4th. Our degree is 4. And in this situation, what we have is we have a bottom heavy situation. And if we look back up at our chart, what that means for us is that bottom heavy means that we have a horizontal asymptote at y equals 0. If we look at our last example, what we see is that in our numerator, we have 6x, so we have a degree of 1. Our denominator, we have 8x cubed, our degree is 3. And it looks like we have a bottom heavy function again. And what we said when we had a bottom heavy function is that we have a horizontal asymptote, and it's at y equals 0. So now that we've done the examples, I know that we ran out of time earlier for our case 3. I want to go back and look at case 3 for a couple minutes. So look back at the top of your paper. And once again, what's happening here is we're looking at the degree in the numerator, if the degree of the numerator is 1 more than the degree in the denominator. So this is a top-heavy situation. And you can pause the video and type these functions into your calculator. But if we look at the first picture here of the 2x squared minus 1 divided by x, we get a picture that looks like this. And if we type in g of x equals x squared divided by x minus 1, notice that x squared, our exponent, our degree in the numerator, the top of the fraction, is 1 more than the degree in the denominator. And we get a picture like that. And then finally, when we type in our third function here, we get this picture on the calculator. And we want to figure out what's happening. And we've seen the summary down below in our notes, but what's happening what's happening to the y values as x approaches negative infinity or x approaches infinity? Well, they're both going towards negative infinity or infinity. But if you look back at these graphs, what's happening is that it's following a pattern there. Or we're following a line there. Or we're following a line here. So how can we describe that when we're looking at the conclusion? What happens to the y values as x approaches negative infinity and x approaches infinity is that the graph is approaching negative infinity or positive infinity, but it follows a slanted line. So just to review one last time, as we finish this video here, the three situations, the three cases are when we have bottom heavy, we have a horizontal asymptote at y equals 0. That means that the degree on the bottom of the fraction is bigger than the degree on the top of the fraction. Case 2, we have the same degrees in the top of the fraction and in the bottom of the fraction. And then in that situation, we also have a horizontal asymptote. And we saw our example where we end up with y equals a over b, where a and b are the leading coefficients of the highest power term. And then finally, if we have a top-heavy equation by degree 1, so the numerator is 1 degree more than the denominator degree, then we end up with the oblique or a slant asymptote. There's that slanted line idea that we just saw. And we have an oblique asymptote in the form of y equals mx plus b, which we're going to talk about more as we continue through this unit.